Equations that I want you to write are for the double replacement and the single replacement reactions only.
Okay. Because I could have sworn I asked you, and you said it was just it was just lab 7 we needed to do.
No, well, the single replacement and the double replacement, there are going to be some, like for example, lab 6, there were what was it, 6 or 7, there were only double replacement reactions in one of those, and so that's why.
Okay. Oh, there.
Yeah, it's both. There weren't that many that we did that followed the single replacement, double replacement form.
Now we're not turning in last week's lab tomorrow. We still need to work on that, right?
Right. It's going to be 2 points. Okay, so let's talk about magnetic properties right now.
Oh, are we already jumping into the chapter?
No, this is from
Homework question. Okay.
So there are 3 magnetic properties that we usually worry about or think about. One is diamagnetic. In diamagnetic compound or atom or whatever you're looking at, diamagnetic means all the electrons are paired. When all electrons are paired, so for example, hydrogen has an unpaired electron. This is not diamagnetic, whereas helium has all paired electrons. That would be diamagnetic. And so we just look, are there any unpaired electrons in the orbitals? If there is, then it gives it a magnetic property because that's a north and south pole. But if they're all paired, then they cancel here. And when we have all electrons paired, then these are weakly repelled by magnets. If we look at a paramagnetic material, we're going to have electrons that are unpaired, one or more unpaired electrons. So here, hydrogen would be paramagnetic, helium would be non-paramagnetic. And these are going to be attracted. It depends on how many unpaired electrons. The more unpaired electrons, the stronger the attraction. So nitrogen, for example, has 3 unpaired electrons unless it bonds. Atomic nitrogen does. When it bonds to another nitrogen, it's diamagnetic. And so this is attracted magnets. And so, for example, if we had atomic nitrogen, which would be 1s2, 2s2, 2p3, atomic nitrogen would have 3 unpaired electrons, so it would be strongly attracted to magnetic fields or magnets. However, if we look at diatomic nitrogen, we look at the Lewis structure for diatomic nitrogen, it has a lone pair on the nitrogen and then 3 bonding pairs, and so all paired. So molecular nitrogen, or N2, is diamagnetic, whereas atomic nitrogen, is N, would be highly paramagnetic. Does that make sense? Yeah. And so we can see the behavior towards magnetic fields or magnets. Paramagnetic materials are interesting, where you have these little crystals. So this would be a little crystal here. Xtal just stands for a small crystal here, or crystal in this case. And this would be paramagnetic. Now, if I bring another paramagnetic material close to it, what happens is the interaction is strong, so if one's up, the other flips down. It's like bringing two magnets together. When you bring two magnets together, North Pole to North Pole, they tend to flip. One of them has to flip. And so if I bring another small crystal to this and it gets very close to this, then one of these flips. However, if they're big crystals like this, then it doesn't really matter because they don't interact too strongly. So if we have a paramagnetic material, it could be pointed in any direction. So this would be big crystal. If the crystals get small, then they tend to flip like this. This would be small. And then you have the just right crystal. Just right size crystal would be like Goldilocks or something, the Goldilocks crystal, in which this would be like Hund's parallel spin. And so if you get all the crystals with the magnetic, what they call the magnetic moment, this little magnet bar here, all pointed in the right direction, then we could get ferromagnetic material. And this is called a permanent magnet. So iron could be magnetized like this. And so that's it. So sometimes when we're looking at electron configurations, we can tell, like chromium. If we look at chromium, how many unpaired electrons does chromium have? So if we go to argon, with 4s, by 3d, 5. So how many unpaired electrons does chromium have? 6. And so what you do is you can take a sample of chromium and then you can use physics to calculate how strong the magnetic attraction is. What they have is they have a special balance, a Gouillet balance. A Gouillet balance, you turn on the magnet and then it pulls. And then you can measure the force of that pull. When you measure the force of the pull, it depends on how many unpaired electrons you have. So we have two choices for chromium. To be argon, 4s2, 3d, 4. This difference in the number of unpaired electrons can be measured using a Gouillet balance. So if you have chromium with 4 unpaired electrons here, it's going to have a much weaker pull than chromium with 6 unpaired electrons. And so with chromium, they verified this experimentally. Otherwise, we would have predicted this. We would have predicted off-bound principle to hold, that is, fill the lowest energy before filling the higher energy. But what's observed experimentally is this. This is more paramagnetic than this. And you can tell that using the Gouillet balance. That's one of the uses for this. Okay, other questions?
I had some homework questions as well. One of them was chapter 12, number 35.
Chapter 12, number 35. All right. Can you read out the question if you have that there?
Yeah. What are the meanings of the terms localized and delocalized when used to describe electrons in a compound?
What is the meaning of delocalized and localized in describing compounds? So, for example, this isn't a compound, this is an element, but we can also have alloys, which would be mixtures of metal atoms. But metals are the classic. These have delocalized electrons. Not all the electrons are delocalized, just delocalized valence electrons. The core electrons are localized in their orbitals. And so with the metals, the core electrons and the nucleus are stuck here. So this would be the core and the nucleus here. And let's say the net charge is +1. So this would be like sodium. How many electrons does sodium have? Sodium has 11 electrons. 10 of them are core electrons, the neon core. And so there are 11 protons in the nucleus. And the core electrons. Well, where are the core electrons? Well, the core electrons are stuck in orbitals. The core electrons would be stuck in which orbitals? Well, what are the orbitals for neon, the core? It would be 1s2. So you have 2 electrons stuck in the spherical 1s orbital, like this. And then what comes next? 2s2. And you have 2 more electrons stuck in the 2s, which is bigger. Even though it's bigger, it's still localized because it's stuck on the nucleus. It's not moving anywhere. It's going to stay at the nucleus. And then what? 2p. 2p. So you have a dumbbell with 2 electrons. That's localized. And we have 3 of those. So 2p, 2, 2p2, 2p2. So we have those electrons localized in the orbital. But the valence electron, the 3s electron, is delocalized. The 3s electron, it has to do with how the orbitals are. But the 3s electron are free to move. So this is what model was this called? The
Electron C.
electron C. And so that 3s electron is totally delocalized. However, all the other electrons are localized. The localized electrons are stuck in a position. They can't move. If you can give a little bit of freedom to the electrons, then we can have delocalized. We call these delocalized pi electrons, or delocalized, I'll get some compounds here. The other case of delocalization is delocalized pi. This is like pi, not 3.14 pi, but a different pi. Delocalized pi. Pi are double bond electrons. So let's take a look at delocalized pi. Usually people call it delocalized pi bonding electrons. So sometimes they do something like this. This is the classic delocalized pi bonding electron. They show that the double bonding electrons are actually spread out over the entire structure here.
In our class.
Let's see. So this video is delocalized pi electrons.
And we're also going to compare two theories on water. Let's start with a review of resonance structures. Resonance structures occur whenever there is more than one possible Lewis structure for a molecule or ion. Here we have the three possible Lewis structures for the carbonate ion, each with a double bond in a different location. So therefore, there are three possible resonance structures for the carbonate ion. Next, we look at the Lewis structure for benzene. Benzene has the molecular formula C6H6. As you can see, there are two resonance structures for the benzene molecule.
So there's a choice in where you put the double bond. You know, here they have it between these, and these, but we can easily made it between the other carbon positions there. So there are only two possibilities for the three double bonds that are going to occur in this. The common name for this is benzene. The benzene was in the news recently.
Yeah, I saw.
Yeah, you know the
I saw.
water-free shampoo, waterless shampoo. It's all recalled because they found small quantities of benzene in there. Benzene's a carcinogen. They said, at least in the story I read, they said the amounts were so minuscule just out of abundance of caution, but still you don't want benzene in there because benzene gets, because of its shape, this thing is just flat and like a pancake. And so one of the problems is this thing gets wedged in one of the grooves, your DNA or RNA or whatever in the helical structure, can cause trouble, cancers, it's carcinogen. Benzene, back in the 1970s, was completely banned. You know, benzene is a very common organic solvent, and then they completely banned it because they were so worried about cancer at the time. And Perrier, did you hear about Perrier? They found benzene in Perrier sparkling water, and then there was a whole big thing about that. And then they finally allowed it again because benzene is an incredibly versatile solvent. You know, it's a liquid that dissolves lots of things. And so it's a great solvent. And so they use it. Benzene, you can find, benzene's probably in gasoline. So if you inhale gasoline vapors, you probably just inhaled a little bit of benzene.
I was reading also too, you know, the water filters like Brita.
Mm-hmm.
They say they remove benzene from water, and I guess the filter is made out of carbon.
Yeah. Yeah. Activated carbon. Activated carbon has lots of pores and whatnot. And it can absorb benzene molecules. So yeah, that would work. Activated carbon. Most water filtration systems will have like activated charcoal or activated carbon to remove organic contaminants like this.
So benzene is also in tap water as well?
Well, they measure it. The benzene can't exceed a certain level in tap water. I don't know what you know, they have a report card that they send out. So let's see what the water in Torrance is like. Torrance Water District has a report card, I think. I don't know what water district is it. It should be published. Well, here's a beach. No, it's beach. This is let's see how much benzene there is. So they usually have a report card and they list how much.
Hopefully there's not much benzene. Aluminum, arsenic, barium, chlorine, fluoride, alpha particle radiation, beta, MTBE, methyl tert-butyl ether, nitrate, radium, turbidity, uranium. Probably, yeah, either they can measure for it or depends. I know other water districts will have benzene on there.
So is benzene caused by like the oil refineries?
No.
No.
I mean, it's not necessarily that. I don't think there's all that much in like in gasoline. There are a lot of benzene derivatives in gasoline, but there's not that much benzene. It's primarily manufactured or used in organic chemistry. Okay. Wikipedia. You can read more about it. Benzene harmful. Yeah. People that were using it in the 1970s were breathing, inhaling lots of benzene vapor. You know, they weren't really treating it with much caution. Benzene is among the 20 most widely used chemicals in the United States. It is used mainly as a starting material in making other chemicals, including plastics, lubricants, rubbers, dyes, detergents, drugs, pesticides. In the past, it was also commonly used as an industrial solvent, a substance that can dissolve or extract other substances, and as a gasoline additive. But these uses have been greatly reduced in recent decades, so you don't find much in gasoline. Benzene is also a natural part of crude oil and gasoline, therefore motor vehicle exhaust as well as cigarette smoke. I don't know where it came. I mean, how it got into Perrier sparkling water. They really don't make the analysis, you know, the analysis of those. It's not legally required. And so you don't know how much it just has to be under a certain limit, I think. And I'm sure there are people testing it. All right, let's continue with this. Benzene is a classic example of delocalized
And each
electrons.
resonance structure has alternating carbon-to-carbon single and carbon-to-carbon double bonds. The carbon-to-carbon single bonds are composed of one sigma bond, and the carbon-to-carbon double bonds, they are composed of one sigma and one pi bond. Resonance structures are a feature of the valence bond theory. In the valence bond theory, the pi electrons are localized between the nuclei of atoms. That means that the pi electrons which form this carbon-to-carbon double bond are localized between these two carbon atoms. One of the problems with the valence bond theory is that these carbon-to-carbon bonds in the benzene molecule are actually equal length and equal strength. So the benzene molecule does not feature alternating carbon-to-carbon single and carbon-to-carbon double bonds. So we're going to look at another bonding theory that more accurately describes the bonding in benzene. Here we have the resonance hybrid structures of the carbonate ion on the left and the benzene molecule on the right.
So these are like the hybrid structures we drew out, you know, where it's 1 1/3. This would be a 1 1/2 bond. But what we have is we have the double bonding electrons delocalized over the entire ring here. And the double bonding electron is delocalized over the entire structure. So that's what it means to be delocalized. That delocalization gives additional stability as the electron cloud can spread out over the molecule. Does that kind of answer pretty much, yeah. And so we have localized. We still have the localized. The single bonds are localized. We call those single bonds the sigma bonds. And the double bonds are pi. The pi ones are what's being delocalized. So we say delocalized pi bonding electrons or delocalized pi electrons. There are different ways of representing it.
In resonance hybrid structure, the bonds go at a double bond.
So
The circle in the middle.
this is how a lot of people represent benzene. They just write this circle here to represent the double bonding electrons are totally delocalized over the ring. Yeah. And so sometimes you'll see that in this case. Okay, were there other questions?
I do.
Mhm.
Or Lily, did you have more?
Yeah, I had one other question.
Okay.
On chapter 11, number 7, it's what kind of light would atoms emit if the electron energy were not quantized, and why?
Okay. What kind of light would be emitted? Well, here, think about the electrons here. Can these electrons move at any speed, through the metal? Like, for example, it can move slow and then a little bit faster, and then forbidden, and then a little bit faster than that. What do you think? If you visualize the ocean, the sea, can the water move at any speed? Let's say a tidal wave comes in. Is that forbidden or is that allowed? Are there allowed wave sizes in the ocean or forbidden ones? What would your...
Move at any speed.
It can move at any speed it wants. You have a wave that moves from, let's say, Japan to the U.S. They can calculate. I mean, it can move. There's no forbidden. So if the wave is moving, let's say the wave is moving at 50 miles an hour or 30 miles an hour, it can move any speed. It can go a little slower. It can go a little faster. There's no forbidden. Right? And so an electron in metal, which is delocalized like this, can move at any speed. Well, if it can move at any speed, then that's what we call a continuum of energies. And so a metal should emit the full rainbow of colors. And in fact, that's what we see. We heat a piece of tungsten metal, it emits the full rainbow of colors because the electrons are delocalized. They aren't trapped in orbitals. However, if these electrons were trapped in orbitals, that is, they weren't delocalized here, then there's going to be a jump between one orbital because the next allowed orbital is going to be higher up. And so this is the difference. Have you seen the sodium lamp? This is sodium metal. But the other day, I was in a parking lot, and they had sodium lamps. And the sodium lamps are going during the day. Sodium lamps are really bright, and they're really efficient. They used to use them as night lights, street lamps, all the time. They gave off that orange light. Are you familiar with the orange light from the street lamps? Well, that's because they have sodium vapor lamps up there, and the sodium sodium vapor is gaseous sodium atoms. And these gaseous sodium atoms, now the electron, at least the valence electron, is no longer delocalized. The valence electron is actually localized. And so if we look at sodium, an atom of sodium has that valence electron stuck in a 3s orbital. Now, what's the next higher energy? Is the next higher energy just a little tiny bit higher than this? And then it can have any energy it wants? Like, it can go up a little bit, or it can go up a lot, or it can go up any amount it wants. No. The next allowed energy is actually going to be like in the 3p. It has to jump up here. Whereas the next allowed energy in the delocalized, in this electron C, is any energy it wants. It could just move a little bit faster, a little bit slower. And so this is quantized. And so sodium vapor lamp, let's take a look at the sodium vapor lamp, maybe. is interesting here. So basically, this is when we do the quantum mechanics, there's a bit more math involved. And so this is written in a different way. The orbitals are written in a different way to show there's allowed, in fact, there are allowed transitions. So for example, you might think we can jump from a 3s to a 4s. A jump from 3s to 4s violates quantum mechanics because there's something that deals with L, angular momentum. There has to be a change in angular momentum here. We jump from 3s to 4s is forbidden. The jump from 3s to 3p is allowed. And so when they do this kind of stuff, then they put all these codes on here to show you what's allowed, what's forbidden. And so this is coded in the way to show that kind of thing, what's happening with the L's and everything else. And so these are all the allowed transitions for electrons. It can't just jump to any orbital. This is energy in electron volts. So this is called the sodium doublet here. The amount of light that it takes for that 3s to jump here is in the yellow, orange. The advantage of a sodium vapor lamps, low pressure sodium vapor lamps contain a small amount of sodium, which takes a few minutes to vaporize, but it's very efficient. If you look at the efficiency, lumens per watt, it's up to 200 lumens per watt of energy, which is why they use sodium. Even though the sodium gives off that orange light and it's not like nice white light, it's very bright and it doesn't cost much energy compared to incandescent. Incandescent light bulb is 4 to 20 lumens per watt. Even a metal halide lamp, which is a halogen lamp, it's still only 80 to 125 compared to a sodium lamp. Oops. Here are the transitions. Here's the efficiency. This is very efficient. 200. But the light, you get this orange cast on there. Looks like this. And that's because it has the specific transitions in here. Actually, this is 2 lines here. It's kind of blended in one. But this one only emits one color of light. Red, actually, let's go here. Red, green, orange, yellow, whatever. RGB, yellow, orange. So this would be in the orange. And so we get a line spectrum like that. And so the output, the light from here is in the orange. Whereas the light from, if I heat a piece of metal, we'd expect a rainbow of colors. Red, orange, yellow, green, blue, indigo, violet. Rainbow colors. So let's show that here. Actually, there's some more. This is not the cleanest. You don't see a rainbow of colors from a low pressure sodium Actually, I don't know what this green and blue. The primary lines are these two right here in the middle. I guess there are other lines from the other transitions. That's a low pressure sodium lamp. Here's some other lamps. The top would be if the electron can have any energy it wants, like in this electron C picture. You know, all metals, when they get hot enough, should be glowing white hot and emit the full rainbow colors. When you add up that total rainbow there, it gets white light. Hydrogen doesn't emit all colors, just 4. Neon emits a lot more because of that orange. This would be an iron atom. Iron metal would be like this. Delocalized valence electrons or whatever. Iron atoms would be like this. And so this difference between iron metal, which has localized electrons, iron metal, which has delocalized electrons, and iron atoms, which have localized. So this should be iron, atomic iron. And so atomic iron would have this kind of spectrum. Whereas metallic iron, should be the rainbow colors at the top. If it doesn't oxidize or melt, so you have to protect it from oxidizing and melting. I don't know what, the melting point for iron might be too low to get the full rainbow. Okay, does that answer it or someone or not?
What about energies that are not in the visible spectrum?
You don't have to talk about that, but the energies that are not in the visible spectrum would start off with IR here. And when you heat up a piece of metal, it might not be glowing, but it'll be radiating heat. So, for example, I don't know if this is hot, but what I do is I hold my hand around it and I try to sense infrared radiation. It's like, infrared radiation, you can't see it, but you can feel it. So, for example, if you're in the shade here, let's say the sunlight is over here, but you're in the shade. If you stick your hand out, if this is the sun, if you stick your hand, you can feel it out here in the sunlight. There's going to be a big temperature difference between the shade and the sun. And so in the shade, it's cold. In the sun, you can feel the infrared heat. And so, there's going to be infrared radiation emitted here. And so, like, a metal will start emitting infrared. We call these black bodies, not just metals, but this is called black body radiation. Why black? Because black bodies absorb all colors of light. If black bodies absorb all colors of light, they should emit all colors of light too. If you excite the electrons. So, hold on. And these are called black body emitters. And so, if you got a black body a little bit hot, it starts emitting infrared. If you get a little bit hotter, it starts glowing red, orange, yellow, and eventually it glows white hot. And then if you continue heating up the electrons, what should it do? It should start emitting what? Ultraviolet. And eventually it should emit X-rays and then gamma rays. But there was a problem because even though this is a continuum, there's still quantized energy levels. And so there's something funny that happened in the ultraviolet with black body emitters. And the intensity of ultraviolet radiation was much lower than what was predicted. And they called this the UV catastrophe. So, it's not you know, what I was saying about light bulbs and this stuff is not perfectly this. So this is kind of backwards here from, let's see. This is kind of backwards here. So we start off with longer wavelength, lower energy. So red's out here, and then as we continue going higher and higher in energy, it goes red, orange, yellow, green, blue, indigo, violet, and then what? Ultraviolet. So this is infrared radiation here. And so this is what you expect. But from classical physics, they expected much more intensity here. This is from Rayleigh-Jeans law. Classical physics predicted much higher intensity over here. So even though this is continuum and we get a full rainbow and this produces white light, it doesn't behave as we expect a totally free electron to behave. So these electrons aren't totally free, even though it seems to be free in the ocean of electrons. And so this is termed the UV, or the ultraviolet catastrophe, because it was a catastrophe for classical physics at the time, because classical physics should be able to predict, and it wasn't able to predict. And so that's a catastrophe, called it in physics. And so there are lots of things on the ultraviolet catastrophe. This is one of the first things that made people realize that classical physics was unable to deal with this type of stuff. This is the black body spectrum here.
So this ultraviolet catastrophe, put it in real world example, would that be similar to wearing like a black sweater in the summer, or it like makes you feel hotter?
Not the ultraviolet catastrophe, but yeah, the black. The black will absorb more. And in fact, it'll absorb, black should absorb all the colors of the rainbow. So, have you heard of this new paint that they come up with? There's a new paint. And I was thinking, I want to get some of this new paint. Not the darkest black. That's pretty cool. They have the darkest black paint. Have you seen the darkest black paint? I mean, things go invisible. You can't see anything with the mask, right? You've seen the YouTube videos on that? Well, now on the opposite end, they have the whitest white paint. The whitest white paint reflects all the colors. Like the current white paint absorbs a little bit of visible. That absorption of a little bit of visible causes things to go up in temperature. And so they have this one. So this is the world's whitest paint. The paint is an improvement of an earlier formula, but this is the ultra white paint. And with this ultra white paint, it keeps things 90, like, the key was barium sulfate. Barium sulfate is a chemical you make in Chem 1A, so you'll actually make barium sulfate. It's a white precipitate. Apparently, I guess it's a really white precipitate because this is white as white. But it can reflect 98.1% of sunlight and cool surfaces by up to 19 degrees Fahrenheit compared to the surroundings. So if you have a black car, it's going to get kind of hot, you know. But if you have this white paint on your car, then it keeps things cool, more efficient, energy efficient stuff. I have a car with no air conditioning. Put this white paint on, at least on the roof. It was probably too expensive though.
I remember hearing 2 months ago that some cities were thinking, well, not actually thinking, they were painting reflecting the orange.
Oh yeah, that's a great idea.
Yeah, I recently went to Home Depot for screening on the door, and they have this one netting that absorbs the sunlight, so that way it keeps your house cooler.
Oh.
It's meant to, you know, the sliding door where you could open it, and it has the screen mesh, so that way you feel the breeze and everything. But yeah,
Oh, that's pretty cool. That's interesting. I think a lot can be done with that. You know, there's that. I don't know though if somebody has their car painted with the whitest white, if it blind you, you know, as you're driving behind it or something. It's too bright. But they're taking some measurements here. White paint samples on a rooftop. What is this one? 97.9%. A thickness of 150 microns. Some of these paints have to be applied too thick, so it's not very efficient. This just came out recently, October 5th, 2022. Interesting. Okay, did that answer the question, I think? Ultraviolet catastrophe, you don't really have to worry about the ultraviolet catastrophe. So I wanted to talk a little bit about tomorrow's lab. Okay.
For selenium. Yeah, we're supposed to write the what is it called? Sorry. Blanking out here, help me out. The 1s squared and
The electron configuration.
electron configuration. I wanted to understand why sometimes, and same thing with chromium, why you would have a 4s to the 1 and a 3d5 if the d can hold up to 6.
Okay.
And the same thing with selenium.
Well, selenium doesn't do anything funny. Selenium electron configuration should be straightforward. You just base it off the periodic table.
Okay, I think I see that, but for chromium, definitely wanted to know why towards the end of the electron configuration it'd be 4s1 and 3d5. D10.
Yeah. Sometimes sometimes things are unexpected. They happen. You don't expect it to be like that. Let's see if they have the electron configuration.
So 3 can hold up to 6 and D can hold up to 10, right?
Yes.
Yeah.
Oh, here it is. The electron configuration is argon, 4s1, 3d5. The reason is this, and it might seem kind of funny, but what would you rather have? Let's say a 1-layer cake with a slice removed out of it, 1/5 of it, 20%.
or one layer cake that's complete. You know?
Complete, but if that's the case, then the S should be complete and the D should be.
Well, the S is a little bit different because the S, what shape is the S orbital? It's spherical, like this. So if you remove half of this, let's say, we take off half of this, it's not like this. And so we don't end up with something like that. What we end up is, if you remove half of this, then we just get a smaller one. Not like that. And so it's like the D orbitals. The D orbitals you can think of as being a two-layer cake, like this. If we cut this in half, we don't slice it down the middle like this. If we cut it in half, we just remove one of the layers, like this. And so it retains that symmetry here. And so it has to do with the symmetry. When you add up all these d orbitals, they have a certain symmetry. So the s orbital has spherical symmetry, we call it. So just a circle, spherical. If you add up the three p's, that also has spherical symmetry. And so all three p's combined will have this. Here, let me grab this book here. I forgot to record the video for that one. All right, it's not enough time. So what happens in Chem 1A, if you overshoot, the endpoint is when it goes from colorless to colored with a half a drop. If you overshoot this, then you typically have to start over from the beginning. But for Chem 4, we can just overshoot it and then go back. Undershoot a little bit, then overshoot it again. So back and forth until we can get a good value. And then what we'll do is record the total volume of sodium hydroxide and the total volume of hydrochloric acid in order to do this. This would be the endpoint of the titration. So then we're going to do some calculations for this. Now, the standard solution for hydrochloric acid has a well-known concentration. It's 0.1050 molar. 0.1050 capital M. So this will be our calculation. So we want the V total for the HCl. This is going to be V final minus V initial for the HCl. And then we want the V total for the NaOH. It will be V final minus V initial for the NaOH solution.
So what we're going to do is we're going to try to determine the molarity of the sodium hydroxide. The molarity of the sodium hydroxide, we want to do this, 0.xxx moles of sodium hydroxide per liter of sodium hydroxide solution. When we calculate the total volume, this is going to give us the volume in milliliters. And so what we're going to do is we're going to convert that into liters here. And that'll give us this. Milliliters to liters. And so the liters of sodium hydroxide, this just comes from the burette. The moles of sodium hydroxide, this is going to come from stoichiometry. And what we're going to do is we're going to start off with how many milliliters of HCl we have. And so we're going to use XX.XX milliliters of HCl solution. And then we're going to convert that to liters of solution by this conversion factor. The liter is equivalent to 1,000 milliliters. And then from the liters of HCl, we're going to use the molarity. The molarity is 0.1050 moles of HCl per liter of solution. And so the capital M just means that we have that many moles per liter. So this is 0.1050 capital M. Okay, this thing we're going to divide. And then we're going to use the mole ratio. The mole ratio is, it's a 1-to-1 mole ratio. 1 mole of sodium hydroxide for every 1 mole of HCl. And so in the numerator, we'll have moles. And in the denominator, we're going to have 0.xxx. We have 4 sig figs, x liters of NaOH solution from this calculation we do here. Okay, once we do that, then we get the molarity. We should have the molarity of sodium hydroxide to 4 sig figs. So we're going to get .ZZZZ. I should have used different. Pull this Y. It's molar sodium hydroxide. Okay, this is the experimental. The molarity of the sodium hydroxide is actually known. And the molarity of the sodium hydroxide is 0.1099 molar. And so that's it. Experimental, the actual molarity is 0.1099 molar. And then we're going to calculate the percent error. The percent error is going to be the actual minus the, actually, no, not the actual, the experimental minus the actual molarity divided by the actual molarity, the actual being the theoretical times 100%. And so we can see how well this titration worked by doing this calculation here. Normally we don't have this number, but what we want to do, the primary purpose of tomorrow's experiment is to get good at titrations. In Chem 1A, they're going to grade you on how good you are at titrations. And so we want to get as much practice as possible. So what we're going to do is we're going to try to fit in as many titrations as we can do tomorrow. And then we're going to do calculations here to see how well we do. Okay, any questions on tomorrow's lab? Okay, if there are questions, ask me tomorrow.
So that over there is NaCH or NaOH?
NaOH. All right, I need to go back to chapter 12, is it? Chapter 13. We're going to look at this. We did 13.1, drawing Lewis structures, and then 13.2 to 13.6. Actually, we're going to look at electron geometries and molecular geometries. So let's take a look at the shapes of molecules. The simplest way to determine shape is using VSEPR. VSEPR is commonly pronounced VESPER. So if we do VESPER, VESPER stands for valence, shell, electron, repulsion, electron pair, repulsions. Pair, I should put in quotation marks. Instead of calling electron pair, we will call this term electron group in our jargon, electron group. Because it doesn't have to be a pair. It can be a single electron or two pairs or three pairs of electrons. All those are considered an electron group. So what are electron groups? Electron groups would be like this: a nitrogen radical, lone electron, it's called a radical. Or we can have a lone pair of electrons, this lone pair. So for example, a lone pair, we don't split up into two radicals. We just leave it as a pair. We could have a single bond group. We could have a double bond. Double bonds are shorter than single bonds, interestingly, and triple bonds are even shorter than double bonds. Try to show that like this. We have a triple bond. With double bonds and triple bonds, we don't split these up. So double bond just counts as one group. Even though it consists of two pairs of electrons is not equal to two groups. So since two pairs of electrons aren't equal to two groups, this is why a lot of people change electron pair to electron group. Because some people get mistaken into thinking a double bond is actually two electron pairs, which it is, but it doesn't behave in terms of two individual pairs of electrons. It behaves as one collective double pair of electrons or double bonds. And the same thing with triple bonds. We don't split those into three groups. All these consist of one group of electrons. Now, electrons have negative charge, and so the groups try to spread out as far apart from each other as possible. And so our book uses this thing with balloons. Or sticks in this case. So if we have two balloons, two groups, they want to get as far apart from each other as possible. So what they do is they adopt what we call linear geometry. Linear geometry is just one's on one side, the other's 180 degrees apart from it. If we have three groups, we'll squeeze another balloon in here. The third balloon is going to cause this to go what we call trigonal planar. So the third balloon coming here, it's going to push these other two apart. So was trigonal planar. A fourth balloon, let's bring a fourth balloon on top, pushes these three down. So fourth balloon pushes these three down. This is called tetrahedral. That's a very spherical symmetry to it. And so linear, trigonal planar, tetrahedral. Those are what we call group geometries or electron pair geometries. And I'll start calling them just group geometries. And so here's what they look like in terms of sticks. So each stick represents a group. These are not single bonds. These could be single bonds, double bonds, triple bonds, lone pair, whatever. These are just separated. So if I have two groups, they're going to separate from each other at a 180-degree angle. And that's going to get the two groups as far apart from each other as possible on opposite sides. If I have three groups, then I'll have to squeeze a third group in here and then spread things out as much as possible. That's going to be 120 degrees in a flat plane. If I have four groups, then it adopts more of a three-dimensional rather than two-dimensional structure, like these two here. This three-dimensional, it's going to, fourth group is going to push these three down. So this is kind of like a tripod. Well, all these are the same. These four legs are exactly the same, and this forms what we call a tetrahedron. Tetra is four sides. So if you connect these with a line, we'll make a four-sided polygon. That's the tetrahedron. And hence the name tetrahedral comes from the tetrahedron. So rather than call this electron pairs, we call it groups. If you have two groups, linear, 180, three groups, trigonal planar, 124 groups, tetrahedral, 109.5. Here's a tetrahedron when we connect the dots. But this is what it looks like. It doesn't really look like a four-sided polygon. It's four groups. This is four single bonds. This is methane. Four single bonds. Now, if the groups are lone pairs or radicals, it's hard to pinpoint. Heisenberg, we don't pinpoint those. And so something like water has four groups. It has two lone pairs, which aren't pinpointed. They aren't even shown on here. And then two single bonds. Hydrogen-oxygen single bond here, hydrogen-oxygen single bond. And this adopts a tetrahedral group geometry. But we don't see the tetrahedral group geometry because the Heisenberg uncertainty principle means we don't exactly know where that electron is precisely at each moment in time. There's a general probability it's here or there. And so we have something called the molecular geometry. The group geometry is tetrahedral. The molecular geometry for this is called bend. Versus this, CO2, there's no lone pairs or anything here. CO2 has two carbon-oxygen double bonds, and this would be linear. And so let's take a look at water and CO2. These all see how those structures originate. So when I draw a blue structure for water, I can draw like this. And I see I have four groups, so four balloons around this. Two single bond groups, two lone pair groups. In order to minimize the repulsion between those four groups, I want to adopt a tetrahedral geometry around oxygen. And so I'm going to have one of the balloons, which holds the lone pair, coming up like this. And let's see how I should do the others. Then I'll have another lone pair coming out. This is going to form one of the legs of the tetrahedron down like this. So what I'm making here is this little L. So rather than having a hydrogen here and a bond, I put a lone pair here. And then I'll put a lone pair here at this angle. This angle is 109.5 degrees. So at an angle of 109.5 degrees, I should have the greatest probability of finding a lone pair. Okay, that means one of these is going to stick out. That's going to be this one here. When we draw something that sticks out, we draw it as a wedge. And so I'm going to wedge this, and I'm going to bond a hydrogen here. And then I have another one that kind of goes back and sticks in, and that will be dashed. So this is called a wedge and dash drawing. The wedge shows, in this case, this oxygen-hydrogen bond sticking out, and the dash shows the oxygen-hydrogen bond going in. All right, so as I said before, the electron pairs are not pinpointed here. And so what we have is we have a group geometry. This one comes out, so I'm going to draw this shadow like this, and this one sticks in. And so this is what we say the tetrahedral group geometry. Tetrahedral group. I call it the group. Your lab, you know what the lab calls this? They call this the electron geometry. Or the EG. So the lab was asking, what is the EG or electron geometry? Group geometry, same thing.
When doing the dashed lines to show if they're kind of behind, does it matter if the lines go like fat to thin or reverse?
It matters. We usually, when it's coming out to you or closer to you, it's fatter. When it's further, it's thinner. And so when we do the dash line, it thins out because it's going behind the page or the plane of the board. Not that there's a law for this. You see it both ways. You see people who write a single line. And so, these structures don't really show. When we draw on paper, we try to show it. It's hard to see from this. Here you can kind of see it better. But here, do you see they don't, when they do the dash, this is very common. You have the wedge here, but the dash is just a dotted line. But if we draw a dotted line, that's going in. And so even though I draw the dash like that, it's not mandatory. Here they have it the same size. Here they have it go from small to large, mimicking this in that sense. God, I'm not going to use Chrome for the YouTube, I guess. So different styles.
So we can kind of.
You could draw it anyway. What's this back here? Maybe I'm against convention here. Most of these are going thin to fat. But that could just be a bias here, wedge dash. This is the way I was taught. We draw it. As it goes further away from us, it gets smaller. As it comes closer to us, it gets bigger. So this is the convention I draw here.
Why does it say like finely distorted? Like in Trinity draw?
This one is totally wrong here. Well, not totally wrong. This is highly distorted. The thing is, can you visualize this in 3 dimensions? This is fine. This drawing on the top left is no problem. This drawing here is completely out of whack. It's completely out of whack because this wedge should be pointed up, not down. So if I have, in other words, people do this in organic chemistry. People bring pencils, extra pencils. They bring extra pencils because they start doing this to try to visualize these molecules. And so that second drawing is totally wrong because let's say I have a tetrahedral like this. And so here's my tetrahedral. Something like this. And then if I rotate it so that these two bonds are in the plane, then that means one is wedged up, out, and one's dashed in. And so this is tweaked out of position. And so what we do with this is we can fix that easily. I can fix that structure. If I were to draw like that, organic chemists don't like to write carbons in it because it takes time. Then we'll draw a wedge coming out like this and a dash going in like this. Should make this a little bit longer, but and that's fine. Since that's the case, since you probably can't see it right off, like I see that right off. I mean, this is totally wrong. Probably takes time to do this. And so what we try to do is we try to always draw it the same way each time. That's what I do. To draw it the same way each time, what we do is we put two in the plane, these two lone pairs, one wedged out, one dashed in. So we have two in the plane, one wedged out, one dashed in. No matter how I twist this, so twist that. Same orientation as that. And so here, two in the plane, one wedged out, one dashed in. Two in the plane, one wedged out, one dashed in. No, the one that's wedged out is always on the left here. The one that's dashed is on the right. It doesn't matter. You can draw on the left or right, but always be consistent. So if you're drawing the wedge on the left, always draw on the left and the dash on the right. Here. Two in the plane, one wedged out, one dashed in. So this person is very consistent. They're drawing the wedge on the left, the dash on the right. I drew it differently here. I drew the wedge on the right, the dash on the left. If I draw the wedge on the right, the dash on the left, I'm always going to do the same thing each time so that I'm consistent. Otherwise, if a person who knows structure sees your drawing, they're going to get dizzy because if you have the wedges, out of place and the dashes out of place, then the structure looks distorted. So we got to watch out for that. Some of these, it gets too much, to draw all the wedges and dashes. This is what cocaine here, the strychnine, which is a poison. Some other stuff. Okay, let's compare this to CO2. If we compare this to CO2, the Lewis structure for CO2 looks like this. Actually, there's one more thing here. The one more thing is we can't pinpoint these lone pairs. And so the structure of water looks like this. Here. And we call this the molecular geometry. The molecular geometry is just the geometry of the bonded atoms. Not the lone pairs or the radicals. Geometry of the bonded atoms. In this case, it's bent. Call it. Over here. This is the electron geometry or the group geometry. This is the geometry of all the groups of electrons. E.g., electron geometry. This is the MG, the molecular geometry. We have to figure out both. So when we go to carbon dioxide, it has the same. The electron geometry, we have two groups of electrons. Two groups of electrons, two double bonds. In order to spread apart as far as possible, will be on opposite sides. Carbon. And so here, that's the not the molecular, the electron geometry. We call it linear. And the linear molecular geometry will have an angle of 180 degrees. A tetrahedral molecular electron geometry has an angle of 109.5 degrees. And that's going to impact the angle here. This is the HOH angle is 109.5 degrees, as expected. Based on the electron geometry. Over here, the bonded atoms have the same geometry. And so this would be the molecular geometry. The molecular geometry is also linear. And it's going to have an angle of 180 degrees. Whereas over here, the molecular geometry is set with an angle of 109.5 degrees here.
Molecular geometry because it's showing lone pairs.
Well, the lone pairs are still there. It's just not showing like here. Do you see the lone pairs here? No. The problem is it's hard to pinpoint the lone pairs, and I mean the electrons in the lone pairs. And even if you do, it's only in one instant of time it might be here. In the next instant, it's over here. We can draw a probability electron cloud. However, it's very easy to pinpoint the atoms. So when we pinpoint the atoms, we can just see where the atoms are using instrumentation, and then we get the molecular geometry.
I'm just saying when you do the molecular geometry, like here on the H2O, we don't show the dots. We don't draw the lone pairs.
Oh, I do. Yeah. I like to draw the lone pairs. So when I do the molecular geometry, I draw like this. If I were to draw that one. And then I have one lone pair up here and then one lone pair here. Okay. So this is how I draw.
So then what would differ the molecular from the group geometry?
The group geometry factors in all four groups here. And so it's tetrahedral, the shape. The molecular geometry is what you see with instrumentation. When you shine light on this, we see this bent. We don't see the lone pairs. We just see the bonded atoms. And so,
Why don't you see the same thing?
No, we don't see tetrahedral. We see this, like a boomerang.
But if you were to look,
If you start probing for the electron, then you'd see the same thing, But
yeah, but I'm saying, they're all the same thing. So if you shine a light on group geometry, it's just going to look like the molecular.
the group geometry is what's going to result here. So it is the same thing as this. So yeah, it's the same thing. The structure didn't change.
Yeah.
It's just we don't call it tetrahedral. Because if you were to look at this using instrumentation, you see a bent molecule. This is what they see here. And so when they do the structure of water, they don't see the lone pairs here and here. But the lone pairs are still there because they're influencing the shape of this.
With regards to the bond angle, that's something we have to memorize, or is there a way to predict that for each bond?
Usually people just memorize